Well, welcome to this talk on Azure Service Bus. This is an advanced talk, so I will cover the basics of Azure Service Bus, but I won't take 45 minutes covering the basics. So just to be sure that we're all on the same page. I think for even those who know Service Bus and have worked with Service Bus, there will be stuff that you may not know and it will be handy to know, so we're going to cover those, or some of those, in 45 minutes. My name is Annejan Barelds. I work for 4.net as a Azure architect. I'm a software guy, so I'm a developer. I've been doing that for, what is it? I think 14 years now. And I think a little over 10 years on Azure. And, well, I basically never look back. I really like the whole big set of building blocks that Azure is. So that's doing stuff in Azure is basically what I've been doing since, I think, 2015. So let's dive right in. What is Service Bus and how do I talk to it from code? We will cover the basics. Let's do that now. What is Azure Service Bus? Basically, Azure Service Bus is a mechanism to push messages into queues, or maybe topics, we'll cover those later, and then receive them on the other end. So it's a way to decouple the producer of a message from the consumer of a message. Has the handy benefit that for a message to be produced, the consumer of that message doesn't have to be online and vice versa. So it's kind of temporal decoupling. That's what Service Bus does. So in its most simple form, Service Bus is about pushing messages on one end and then receiving them on the other end. As I said, not all is about queues. You could also have topics. When you also have topics, you also have subscriptions. So you could have senders that push one message into a topic and then have multiple subscribers to that message, so each subscriber gets its own copy. That's basically Azure Service Bus topics and subscriptions. So a queue, from the perspective of the sender, is really the same thing as a topic. So for the sender, it doesn't really matter if it's publishing to a queue, to a topic. For the receiver, the same applies basically to queues and subscribers. So for a receiver to listen on a queue or to listen on a subscription is, in a programming sense of the word, and also kind of the features that you have in interacting with Azure Service Bus, is basically the same thing. When you receive a message, there's roughly two ways of handling that. You could do receive and delete, which is basically your receiver reaching out to Azure Service Bus, receiving a message and saying, okay, I've got it. The message is then gone from Service Bus. There's no way to retrieve it. And it's up to the receiver to make sure that you properly handle that message. That's fast. That's faster than the alternative, being peak lock, but it's also a bit more risky. Receive and delete really means that after your message is received, it is deleted. So if between you receiving the message and you properly processing the message, something bad happens, your message will be gone. Which is where peak lock comes in. Because peak lock enables you to basically peak the message as it's still sitting in the subscription, it's still sitting in the queue. But it's not actually deleting the message from that queue just yet. You have a lock on the message, but the message is still in the queue. You can renew that lock if you want to, and then ultimately, if you're done, you can settle the message. Settling means completing the message, saying, okay, I'm done. I've successfully seen this message, and you can take it off now. You can also abandon the message, which is basically saying, this is a properly formed message, and someone in the future may be able to handle it. Maybe I will be able to handle it in the future, but not now. So I'm abandoning this. Let someone else try. Or you could dead letter it, saying, well, I'm not able to handle it, and no one is, so let's put this one aside. Let's not have that message block subsequent messages. So that's settling. And that's basically, Azure Service Bus 101. Basically the groundworks of what we're going to talk about today. We also want to talk to it from code, obviously. And I'm going to show you a lot of demos that all involve some piece of code. I will walk through the basic setup right now. And let me just, I think this is readable in the back. I checked. Yeah, it's okay. What we will be doing basically throughout this talk, so we'll be visiting this very basic web app that I have. There it is, which is basically, well, it's a web app, and with that web app, I interact with Service Bus, post messages on it, and then see what comes back. So it also allows me to just show how you talk to Azure Service Bus. So all these demos basically start with, and this is not a very nicely architected application. It's just, well, for demo purposes. So basically, interacting with Service Bus from, let's say, a web application or a console app or something would go through an Azure Service Bus client, where you could then create a sender, or maybe you create a receiver. You send messages to it, and that's it. So programming against Azure Service Bus is fairly straightforward. Most of the messages that I will be sending to Azure Service Bus will be handled by an Azure function, and that's basically one of the, well, more predominant ways of interacting with Service Bus. If you're on the Azure ecosystem, you'll probably have functions that react to Azure Service Bus messages. So let's just show one of them. This is just a random one of my functions listening to a queue. And that trigger is basically defined as a Service Bus trigger. And it's now receiving a Service Bus receive message. It's basically triggering this function. I may be able to do some other stuff as well. So I have message actions, so I can defer or complete or something. So all neatly wrapped in that binding. And if I need to interact with the client directly, I can also have that in my function. So that's how you talk to it from code. Okay. One of the assumptions that I most frequently encounter with people that, well, start to understand Service Bus, start to work with Service Bus is, okay, cool, so I have messages, but just let me get this straight. Service Bus does preserve the ordering of messages, right? So, just a quick show of hands. Who assumes that Service Bus will be handling the order of messages? It's a kind of a trick question, obviously, because if it did without any problem, I would probably not be talking about it. But it does, but not in the way that you would expect, probably. The order that's guaranteed in Azure Service Bus is that the order in which you put messages on the queue is the order in which they, well, live in the queue, and also the order in which they will be received by clients. But functionally, that doesn't really buy you that much. So let me start my first demo. So let me just click this. Oh yeah, and just forgot to tell you, basically what all my functions do is, well, besides logging to app insights and stuff, they also put messages on the SignalR hub, so I can basically ingest all of them, these comments that my functions make, basically, back into this UI, so that we can all read along. So these are, what I've now done is I've taken my application, I've iterated from 0 to 9, I've sent 10 messages to Azure Service Bus. I did that in order, so I didn't do it in batch. So we're really sure that I put the one with the 0 first and then the 9 last. And now we're seeing in which order they were processed. What happened here? Anyone? Sorry, who's? Yeah, okay.
Asynchronous execution of functions.
But if it's asynchronous, I would still. Why is it out of order? If it's
No, one processing time is different between.
processing time is different between them, and you say them. Which is correct, by the way. It's multiple receivers. The standard way that a function, and basically any client that receives messages from a queue, the standard way in which it does that is it spins up 16 threads, and it uses these 16 threads to, well, basically process 16 of them at the same time, which is called the competing consumers pattern. So all of a sudden I have these messages in the queue, so maybe the top processor picks up the first message, but immediately after that, the second processor picks up the second message, and that may finish earlier than the first message. So, and that's basically what gives you scale, right? I mean, having this means that you can shove a whole lot of messages in there, and they will be processed by 16 processors. If you scale out your function app, maybe it's going to be 32 or 64 or something. So one of the first reactions to people who actually think, okay, well, yeah, nice that the order is preserved right here, but I need the order to be preserved in the order, in the processing phase, actually. One of the first things that people tend to do is, okay, well, let's then kill that competing consumer. I don't need that scale. So let's just go to one processor. Quick show of hands again. Who feels that that would be an effective way? I mean, it's not a proper way, maybe, but an effective way to force ordering.
It's very effective. It's effective.
Yeah? You feel it's effective? Maybe not proper, maybe it doesn't scale, but you feel it's effective?
In fact, it gets the job done. It's not fast.
And I'm afraid it also doesn't get the job done. So let's try that. And this one and the next one are the only two demos that I don't run in Azure. I run them locally, so I'm going to start up a function locally. What happens is I'm sending again these 10 messages. I have that thing configured as a singleton, so it's running only a single thread. It's processing one of them at a time, but it's basically killing itself at message 5. So then I'll have to restart it, and then we'll see what happens. So first off, let's do, this is the singleton without sessions, yes. I'll start it without debugging. Just waiting for it to come up. So now we're doing this. It's become super slow. We expected that. It's crashing at 5. So that's gone. I'll be restarting it. Oh dear. Message 5 was obviously retried. I mean, we crashed, we were processing it, we crashed, so that lock will expire at some point in the future. And then it will be re-available in that queue. And then it will be processed after message 9. So apart from it not being a proper way to architect, it also doesn't really get the job done. In case something bad happens. I mean, in the happy flow, for sure, but we don't live in a perfect world, so something, if it can happen, it will happen, obviously, right? So a singleton is not the answer. Anyone, any idea what the answer may be? You can do this. I mean, sessions. Who said sessions? Yeah, sessions. So what are sessions then? Let's first go back to the slides and see. Sessions are basically A session is an identifier that you, as a producer of the message, put on that message. You basically label it with a random string, session identifier. And then receivers will receive messages from the queue, but it will log not a single message, but it will get a log on the session. So once a receiver receives a message with a certain session, all messages for that session will be received by that same receiver. Which is the only way to ensure ordering. If we were to put a session, and now the demo that I'm about to show you, I have a single session that I'm putting on all my messages, which is basically the singleton pattern, but then done right. And we'll let's do that first, right? Just to. Okay. So again, this thing is going to crash at message 5. There's this one. There it is. So it's now crashing. So that's gone. We're starting it again. Debug. Start debugging. And now we have them in order. Obviously, it's not a great idea to label all your messages with the same session. So if you, basically the first thing that you should be doing if you feel that you need ordering is revisit that question. Is it really, do you really need ordering? Is there an alternative way to architect your system, architect your process such that you don't need ordering anymore? Because it's complicated. If you really, truly, and unavoidably do need ordering, you could use sessions, but then it's smart to pick a session on something that's, well, has a wide distribution. So let's say a single user ID. If you feel like, okay, I need to process the messages for a given user, maybe in an ordering flow or in some kind of a provisioning flow or something, messages for a single user need to be processed in order, then use maybe the user ID as a session identifier, because then all other users will be eligible for parallel processing. It's just the messages for the single user will be in order. So if you do need ordering, sessions is the way to go. But really ask yourself, do I really need ordering? Make sense? Cool. One of the other things, and that's not something that may be specific to Service Bus per se, but well, is a more general concern for distributed systems, is, well, back in the days of the good old monolith, it was easy to trace all through the system what happened. I have logs that I can correlate quite easily because it's all a single big request that's handling it. Now that I'm using distributed systems and I'm passing messages around, and maybe something doesn't happen immediately, but it takes some time because the queue was filled up, and how am I going to correlate in a functional process? How am I going to correlate all that dispersed execution logic and the logs and the traces that it generates? How am I going to correlate that back to that single request for that single user that reported an error? And actually, this is a demo about code that I didn't write, because I've seen a whole lot of solutions for this problem where people use the correlation ID on an Azure Service Bus message to put in some identifier that by convention maybe means something. And I didn't do all that. But I do have a setup with my web app, the one that we've seen with the buttons and the logs, etc. Then a message that's being received by a function that's then posting another message that's being received by another function that's calling an API, and then all the way back. So it's really a distributed system where we're also switching context 2 times, right? This is HTTP. this is all service bus, and then we're doing an HTTP call again. And the code for that is, let me just quickly, step 1. This is a message. This is a function that's receiving a message. There's all transaction stuff. That's for another demo. But basically, it's creating a sender, and it's sending a message. And I do see that I have a correlation ID here, which is not what I really wanted, because the point is that you don't need a correlation ID. So maybe in step 2 I left it out. Why did I do that? Yeah, so this is just now it's string content. The point is that you can leave all the correlation stuff out. Just do that call. I'm not going to do that live, because before it lands in application sites, it takes a few minutes and stuff. So here's one I prepared earlier. I think this one. Without doing anything, really, I get a call on my web app. This is my demo app. That's then linking to, let's keep that aside. Linking to my function, doing stuff. Then that's linking to another function, which is doing stuff, which is then linking to an API, which is also doing stuff. And that's all correlated back to that same request. Not using correlation ID, but using basically the built-in diagnostics in the SDK, or in the SDKs, plural, actually, because it's both, well, HTTP calls that you do from within the framework. That's also messages that you send through Azure Service Bus. This all happens automatically. You don't have to do anything to get this end-to-end tracing going on. If you shove your stuff into application sites, this transaction search just works. And if you want to know, I won't spend too much time in there, but if you want to know, all the magic is happening through a custom dimension. Where is it? There it is. Operation links. The custom dimension, and technically that's the thing, if you visit this just in the logs and the traces, it's going to be in custom dimension MS link, which is holding a reference back to the original process that basically triggered that message. And it's just a system property that's filled with trace parent and trace context. Trace parent and trace context is a different discussion. That's about distributed tracing. Not going to do that here. But the point is, if you use the ecosystem to your advantage, there's really no custom code, custom correlation going on at all. Not a good one. Messaging is a bit brittle, right? I mean, I like my traditional transactions, my atomic, consistent, isolated, durable transactions. Thank you very much. I was kind of lost on the what the I meant. But yeah, so where's that in a distributed system? How do I ensure consistency? Again, this is maybe not a service bus problem per se. I mean, if you do REST calls, I think theoretically it's possible to do ACID transactions over REST calls, but it's a hell of a job. I'm not sure if it's ACID, but well, you can do. There is distributed transaction support over REST, but that's hard. But somehow, when we do REST, we don't consider that a problem. But once we do service bus and we pass messages around, we start considering that a problem. That's kind of what I found in talking to people. Which is a bit unfair, but okay, well, let's address it. So yes, it's not ACID transactional. there will be hopefully eventual consistency, but it's not as transactional. Still, there are features that you could use to kind of mitigate the problems that come with the fact that it's not fully transactional. I'm going to mention a few. I'm going to show you two, I think. Two. One that I want to just mention is a thing called duplicate detection. Duplicate detection is something that you can enable on a service bus entity, so a queue or a topic. It's basically allowing you to say, okay, well, within a certain time window, let's say 2 hours, if 2 messages come in with the same message identifier, same message ID, then drop the second one. So that's basically a solution to the problem. What happens if you send a message to a queue which is properly processed, but you are not alive anymore to actually receive the acknowledgement? And then maybe you start up again and you reprocess that message, or some kind of variation on that theme. So it's a way to ensure that if you properly identify the message ID as a sender, if you have a mechanism to ensure unicity there, then you also have a mechanism to ensure that you have unique messages on the queue. Another one is, it used to be called Zenfire, and it was maybe more of an SDK kind of nomenclature than it was an actual service bus thing, but it's now called cross-entity transactions overall. And let me just first show you the code and then show you the demo. It's basically a way to ensure that, let me talk through that via the code, that may be more helpful. Where is it? I think here. Yeah. It's basically wrapping the completion of an incoming message. If assume you have a process where you receive a message, you do something, and then you communicate the result of what you did in another message that's going into another queue or another topic for someone else to handle. So a multi-step process. What cross-entity transactions allow you to do is ensure that the completion of, well, your incoming message, so your acknowledgement back to service bus saying, okay, I process this message, that you can do that in the same transaction as the sending of the message for the downstream process. You can wrap that in a transaction. If you use transaction scope, and then you do a complete message, and then maybe you do stuff, and then you send another message. You can be sure if you, that's something that I would almost forget to share, but it is quite important. If you actually enable that in your service bus extensions, or if you enable that in the client that you create, if you create your client outside of a function context. So you have to basically set that flag, but then you can do this. So in my demo, there it is, just to prove the point that it actually works, what I'm doing, and this is a bit of an ugly piece of code, but what I'm doing is I'm sending a message to a function. The function is doing something with it, and if it's the first time it receives it, it will retry it. If it's the second time it receives it, it will just give up. If it's the first time it receives it, and if it's my cross-entity transaction demo, it's actually going boom. And then, so that's throwing an exception, and then in catching that exception, retrying means I'll abandon the message, which means I will be seeing it again, because I'm just abandoning it, and then it will be re-available on the queue. And, well, if I'm giving up, I'm dead lettering it. So, and obviously, as I said earlier, we are actually doing a complete message. So that's the first thing that we do. So we are completing the message, but we do that in the transaction. And, well, if we error out of that transaction, we will never reach the transaction.complete. So the complete will will not have happened. Demo-wise, that means that indeed, the first time the message is being picked up by that function, it's retrying it, means it's abandoning it, means that it did not complete it, proven by the fact that we've seen it again, second time, after which we gave up. We're still in the whole this is not asset transactional, etc. discussion. This is another mechanism to ensure a little bit of transactionality in Service Bus. But what you will probably want to have with any non-trivial situation is something that we call compensating transactions. What you can do, for example, in a multi-step process is, let's assume we have a process that's putting a message on a queue that's being handled by another process, putting a message on a queue and yet another process, and so on and so forth. Maybe something in the universe is going wrong and maybe something is crashing, so what happens then? The point being that in an asset transaction scenario, either it will all have happened or none of it would happen. And that's kind of the situation where we ultimately, eventually, want to reach. Compensating transactions is basically a way to ensure that. And what you can do is leverage the fact that if you dead letter a message, it will end up in a dead letter queue. So let's say that step 2, if it's not able to process a message, the message will be dead lettered, so it will be sitting in a dead letter queue. The same applies to step 3. The dead letter queue can actually, that's for all intents and purposes, is a normal queue in Azure Service Bus. It's just, sitting underneath the main queue. But just as with the main queue that you can configure auto forwarding for a queue, you could also configure auto forwarding for a dead letter queue. I cannot show you that in the portal because it's not in the portal. But I can show you, for example, right here in Service Bus Explorer, you can actually configure the dead lettered queue to forward messages to some other entity. So that allows you to, back to my slides, allows you to create a topology where the dead letter queues will be forwarding to, some other queue, upon which a listener basically undoes whatever step 2 was doing. And then it's putting a message in the queue to also undo whatever step 1 was doing. Or if step 2 already crashed, then we don't bother with this one. We just follow this path. And I have a demo for that as well. Basically, it's part of a larger narrative, hence the fancy names with regress to upgrade and stuff. We're not actually doing the fancy narrative. But I just want to, I think it was right here. Where is it? Yeah, I used to have a randomizer in there, but it was really annoying when you wanted to do demos and then 5 times in a row it just didn't fail. So I'm now just failing in 100% of the cases. So this is step 3. Step 3 is failing, it's dead lettering, and the topology is arranged in such a way that if you want to actually do stuff, maybe my signal R connection is lost. It could be trying that once again. Okay. There we go. So this is basically a very, very, very simple example of compensating transactions using standard features in Azure Service Bus. So nothing fancy, just listeners on queues and auto forwarding configured. There will obviously be situations where even compensating transactions don't help. I can, for example, imagine a situation where you want to, well, you have a business process where you need to save stuff to a database, but then you also need to communicate, maybe publish an event a change in fact happened, so that process did indeed run. Maybe the process resulted in an update to an aggregate, and you want to publish a domain event that's detailing whatever happened to that aggregate. So then you have to get a bit creative. For example, using what's called the outbox pattern. That was it. So I can imagine that your aggregate, for example, is being stored in Azure Cosmos database, and then you use the change feed for Cosmos to publish the events. So then you will still have transactionality in the sense that you won't be in a situation where the commit to the database did happen and the publishing of the event doesn't happen. Yeah.
But the example you just showed with the compensating transactions and the dead letter queues and then the forwarding. So does that mean that there's a dead letter queue, not just one, but one for every queue?
Yeah, one for every queue. Yeah, for sure. Every queue automatically gets its own dead letter queue. Correct. Yeah, I should have mentioned that explicitly, but that's correct. So that's transactionality. It's not ACID, but it is eventually consistent.
Still you cannot compensate for every thing.
Well, it does require a different way of architecting stuff. You don't have ACID transactions, but as I said, you also don't have ACID transactions if you do REST integrations. So and at least if you do Service Bus, then there's all sorts of mechanisms to, basically gain back a little bit of that eventual consistency. With REST, you're basically on your own. So if you think about it, doing Service Bus or another messaging type integration actually gets you closer to consistency and transactionality than you would if you just do REST. Last one, also a frequent flyer in the set of objections to using Azure Service Bus. The claim being that messaging is one way, but our processes are not one way. We are not doing fire and forget. We can't get away with that. We need to have some feedback. Fine, we can do that. Oh, this is an animated slide? Okay, well. It's actually, you can have request-reply structures in Azure Service Bus. So basically what we want is this, right? We want a sender that's sending a message to a queue, someone else is processing that, and then it needs to answer back to us with, some meaningful response content. It failed, it succeeded, this is the result of your calculation, or something like that. And there are a myriad ways of doing this, and I'm just going to show you a very simple one. So this is my web app. It's actually triggering off all these demos. Just let me quickly search the correct one. We're using sessions for this one again. So what we're doing is, as we always did, we are creating a sender, and we are going to send a message to that sender. But what we also do is we will create an identifier, some random string. We label that the reply session. And that reply session is going to be attached to the message that we send. So instead of setting a session ID on that message, we set a reply to session ID on that message. So we are not sending a message on a session, but we are saying to whoever is going to receive our message, please use this session if you feel that you want to reply to me. And before we actually send that message, we start listening on the reply queue. We start listening on specifically that session. So now we have a listener. So we started listening on a reply queue for our specific reply session, such that basically all responses in that reply queue will be ignored, except for the one that we are interested in, because it's a response to our request. We can also do timeouts there. I mean, we may not be interested in the message if it's going to be available past 3 seconds. I mean, we won't wait forever. Obviously, that's very specific to the use case. But that's basically a way to do very simple request reply within an Azure Service Bus, well, architected system, if you will. So that's actually fairly quick, right? I mean, this is... I could have done a REST call, for sure. But you can imagine that maybe the processor is not only listening to our stuff, but it's also doing other stuff, and maybe it's... well, in the interest of time, I won't be able to do the fan-out, fan-in scenario, but you could also imagine that I have one message that needs to be processed by several different entities, and I want to aggregate all the results back and then do something meaningful with that. So that's, given the time, that's going to be stuff for another talk. But let's quickly get into that that reply function. Where is it? It's not here, right? Yeah, there it is. So this is basically the only thing it's doing, apart from waiting a second. It's just really taking that reply to session ID and using that as the session ID for the reply it's sending. So it's just pretty basic. So that's how you could do request replies. And as I said, there are more interesting scenarios than just the basic doing a request response. It could also be REST, but yeah. So to sum up, Azure Service Bus does reliable messaging. If you need sessions, if you need ordering, then you will need sessions. Distributed tracing is really a no-brainer. That's just available. So let's just be done with that issue. There's multiple options to ensure something of transactionality and eventual consistency. And asynchronous doesn't have to mean unidirectional. If you want to take a deeper look at my code, this is where it is. It's, as I said to some early birds in the room, it's not production code, so don't copy-paste it and use it as such, but it gives you some ideas on how stuff can be done. And that's it.